Okay, everyone, welcome back. In this session, we're going to have some more talks about program logics and program analysis techniques for correctness and incorrectness. So our first talk is by Andreas on unified compositional formal methods, and I'll hand it over to you now.
Yeah, great. Okay, so I'm going to talk about the things that we have been up to in Philippa's group lately, some of the people in Philippa's group. And maybe this something could be summarized as the unified compositional form methods, where unified means that we are interested in both over-approximate verification and under-approximate bond finding, and compositional. Test, hello? No? Better? It's apparently only this one. Okay, yeah, so unified or approximate verification and under-approximate point finding, those are the things that we're interested in at the same time. And compositional here meaning separation logic. More specifically, we have invented a unified compositional program logic. This was published last year, and then based on this work, we have also built a unified compositional symbolic execution tool/formalism. But since Philippa is going to talk about the Gillian stuff on Saturday, I'm going to focus on ESL here. So ESL being an abbreviation for exact separation logic. Let's start with an example use case to get some motivation. So this is you, and you're all dressed up because you have built a reusable library, for example, a linked list library. And these are some people, and you're happy because these people want to use your library. However, some of these people are interested in verification, so they want to use your library in verification, whereas some other people only do testing, etc. So you're no longer happy, because this means that to satisfy both of these groups, you would have to provide both separation logic and incorrectness separation logic specifications for your functions of your library. So 2 specs per function. Oh no, if only we had a unified program logic. So maybe I've also noticed the following. So if you kind of put separation logic and incorrectness separation logic next to each other, they look pretty similar. So for example, the heap mutation rule looks pretty similar to me. Well, allocation, see some similarities there. Well, both of them have a frame rule, etc. So it might make sense to, in some sense, work in the intersection of these two logics, formally meaning something like this. So we define ESL triples to be valid if and only if the corresponding separation logic and incorrectness separation logic triples are valid. And this gives us the following proof system. So our rules are sound if they are sound in both these old proof systems. So in some sense this is a new logic, and in another sense it's barely a new logic because it looks pretty much identical to SL and ISL. So in terms of this use case, we can now be happy again, because instead of doing 2 proofs, we can do 1 proof in this unified logic. And if we do a quick comparison between these 3 logics, one could say something like this. So separation logic is a good fit for verification, because the kind of approximation you can do there doesn't allow you to drop execution paths, but it is not necessarily a good fit for bug finding, because you can drop information along execution paths. Whereas for incorrectness separation logic, you have the opposite situation. And ESL is a good fit for verification and bug finding, because there you're not allowed to drop anything. Okay, so after defining this logic, there are some questions to be answered. And I will focus on 2 questions here. Both of them being relevant for both currently existing and approximate separation logics. So ISL and ESL. So to do the kind of specs for functions we wanted to do, we had to think about the two following things. So the first problem, no one had fleshed out the rules for function calls in under-approximate separation logics, and therefore there were no soundness proof for this calls either. And also, no one had thought about abstraction in under-approximate separation logics. So let's talk about these two topics. So first, let's start with function calls in under-approximate separation logics. So this is, well, an example spec and some template function, some program arguments, some function arguments and some program variables, etc. And what is interesting here is that these two things, so the pre and the post, they talk about the external behavior of your function. Whereas when you're reasoning about this thing, the function body, then you will be reasoning about the internal behavior of your function. So a natural question is, what is the relationship between these two behaviors of the function? So in over-approximate logics, these two behaviors kind of coincide, or they are so similar that we barely think about them. And why is that? Well, because the difference between these two behaviors are basically these program variables. And if you have, for example, or if you have the internal behavior, so in the sense that you have done a proof about the behavior of your function body, then it's very easy to derive the external behavior, because in over-approximate logics you can just throw away any kind of information you want. So just throw them away, you don't think about it that much. But in under-approximate logics it's a little more interesting, because there you're not free to throw away whatever information you want. So one way to think about it is that in under-approximate logics you can only drop information when the information is also dropped in the program semantics. But this is exactly what would happen here if you call this function. So at function exit, you do drop information, loads information, in the sense that the program store that you use when you execute this function is just thrown away. So therefore you can reflect this operation into the logic. And this is, well, a little verbose for now, so we can summarize it as this. So we capture this forgetting by a mechanism that we call internalization, which basically allow you to, well, throw away this information that is thrown away in the programming semantics. Whereas the function call rule, when you actually use the specs that you establish, is looking pretty much the same. You just have to be a little careful with the program variables here again to not lose information. But this is right, this kind of looks like the separation logic function call rule. Okay, so then there is this second topic, abstraction. So what do we mean by this? So this confused us maybe more than it should have initially, but after we realized or remembered that abstraction and approximation is not the same thing, it made some more sense to us. So this kind of function specification, where the list predicate here is just the normal inductively defined list predicate, meaning that we have a list in memory which is of length n, and the function is just a list length function. So this spec is valid in this exact separation logic. And why is this? So informally we can look at the SL spec and ISL spec separately. So of course the SL spec is valid. We have seen, well, everyone in here has seen this spec many times in over-approximate logics. But it's also interesting that the under-approximate spec is valid. And why is that? Well, formally we would have to do the proof, of course, but we can reason about this informally as well, because if we cannot find a state in our post that is not reachable, well, then this is a valid spec. And here it's quite easy to see that all of these states will be reachable, because if you take a model of the post, well, we will get some list, and the return will be the exact length of the list. And to reach this, we simply use this model of the post as our model of the pre, and then we get there. So in this case, it's quite easy to say that all of these are reachable. And maybe another way to informally think about this is that in some sense we didn't have a lot of information to begin with, so therefore we do not need to specify a lot of information in the post. So yeah, therefore we do not drop information here, so therefore this is a valid under-approximate spec. And some specs look a little more interesting in under-approximate logics and exact logics. So if you look at a spec where we add an element to the beginning of the list, then it looks a little messier than the spec you would expect in over-approximate logics. And why is this? So it basically comes back to, again, that we are not allowed to drop information. And here it all centers around this x here, x being the pointer into the list. And the messiness arises from our need to describe what happens to this x. And this is probably easier to see if we visualize it. So let's consider this example pre-state. So we have some example list containing 3 and 4, and then we have this x pointer into the list. And then the post state, if we add, for example, 7, will look something like this. But actually, not all of these post states, or not all of these lists that look like this will be reachable, because we had our pointer into the data structure, and this pointer will necessarily end up in the second position of the list. So therefore, we cannot just say that, well, we have a list starting with 7. We have to say that we have a list starting with 7, and also the second pointer of our list is our previous first pointer. Because if we don't include this information, we would over-approximate the reachable states. And to be able to say this, we need to expose all the pointers internally. So this is why this x's is here. So x here is the pointer into the list, the x's are the internal pointers, and vs is the contents of the list. So we still manage to capture, in some sense, the full behavior of the function, but here we have to expose more details than we would have to in over-approximate logics. And another way to see this would be to think about what would happen if we didn't include this listed thing here. So the thing that is restricting where x will end up. Let's say that we actually use the function spec without listed. What would happen then in under-approximate logics? So let's say that we have a list in memory, and then we, for example, copy this pointer into the list into another program variable. So now our state will look like this, and then we have to massage it a bit to fit our function call rule. We just have to take care of the program variable, as I mentioned before, and then we do the actual call. And if we didn't need to describe what happened to the pointer into the list and expose the pointers, then we would have something like this, where we end up in a state where we don't know anything about y. But this is bad because before the call, we knew that y is null, because, well, x is necessarily null if the list is empty. And this is exactly what listhead would say in this case. So if the listhead of the non-existing internal pointers would be there, then you would know that y is null. But so this is some of the things that we had to deal with to be able to actually use this logic for the kind of functions that we were interested in. But then this, I would say, is maybe the most common question people have after seeing this. So do we really want to, well, use a logic without approximation? So for example, our session share puts this worry like this. So, well, is it really practical, basically, to not have consequence forward or backwards? So we can go back to our initial use case and think about what does it mean to not have approximation here. So one way to think about it is that not having approximation is a consequence of the kind of specs that we're interested in rather than our program logic. So we are this person down here very happy because we have this unified logic, and we want to serve these people that want to do both verification and testing. So in some sense, well, if you would over-approximate, then our specs cannot be used for testing, and if we under-approximate, they cannot be used for verification. So we don't have much choice here if you want to at least unify these two logics, being separation logic and incorrectness separation logic. Because if you want to actually capture the full behavior of our various functions of our library, then it wouldn't help if our logic could over and under approximate, because when we reason about these kind of functions that captures the full behavior of the function, well, let's say that our logic could, for example, drop execution paths, that is being an approximate logics. So if we, like in the middle of our proof, just drop some program paths, then, well, in the end we wouldn't be able to show that the actual full post here is reachable. And similarly for over-approximate logics, if you just throw away some information, well, like if you throw away like the contents of the list, well, probably we cannot show that this post is true. But this is just the case for us as library developers. Let's say that we are not necessarily interested in exact specs. So let's say that we, for example, we are this person up here, so we just want to use the specs that have been proved about this library for verification. Well, then you can over-approximate how much you want, because you can just use ESL and you just use our ESL specs in SL because they are compatible. And similarly, if you're interested in testing, well, use ISL and then we'll take the ESL specs from this library and then just derive the ISL specs because they are implied by ESL, because ESL is a strong logic. However, if you're this person down here and you want to provide specs that are useful for both verification and testing, then, well, maybe ESL might be a reasonable logic for this. So, short summary of the paper, we introduced this ESL logic, and then we give rules and prove soundness of how to do reasoning about functions by formalizing this internalization mechanism. And then the paper also contains some more examples of doing abstraction in under-approximate logics. So we provide some specs for example, singly list library and some functions over balanced trees. Yes, that's it.
Okay, we have time for a few questions.
Thanks for the talk. I was wondering about the consequences of having no approximation when you're talking about loops, because obviously in an over-approximate setting you can have loop invariance, and in an under-approximate setting you can just consider like a finite unfolding, forget about other branches. But in this work, as I understand it, you can't forget about branches because it has to be an over-approximation as well. And so is it the case that the precondition has to ensure that you're only considering a finite, that the loop can only be unraveled a finite number of times?
Yeah, so the loop has to terminate, yes.
Okay.
And also so if you have some kind of something that could not terminate, for example, recursional loops.
But is it, regardless of termination for individual instances satisfying the precondition, is it the case that all instances of the precondition together must only enable a finite number of unfoldings? Because otherwise you couldn't talk about all paths without over-approximation.
Yes, the meaning of the triple is basically this. So, well, this is the total whole triple or total subpersonality triple. So it has the usual meaning. So for all states in here, it necessarily terminates in there. And this is the usual ISL triple. You can pick anything there. That must be reachable from P.
Sorry, so it is possible to capture all of the paths without over-approximation. For example, you have the proof of the list length that is fully general. So you can do it. The problem is that then what would happen is that you would really have to precisely describe your loop, which is just fine for list length, but is going to be less fine for the other ones. That's basically it.
You kind of have to include the termination condition in the
Yes,
in the
yes, you will
as
get
well,
it, yes.
in order to ensure that it goes both ways.
Yes, in a sense, yes.
Okay.
You can take a look at the while rule. It should reveal.
Okay, thanks.
Thank you.
Yeah, we have one more question.
I was wondering what this sort of thing means for, maybe this is a general question about incorrectness logic, but it seems like you have to expose a lot of information in your specifications, and that seems to imply like a brittleness to changing the implementation of a library. Like, I'm imagining, your code works out fine, and then someone tweaks the implementation of list to be something slightly different, and then kind of everything breaks. What does that kind of mean for sort of modular program development or reasoning?
Yeah, for example, these kind of specs, in some sense, there's not a lot of abstraction going on here because you expose, well, basically everything, all the internal pointers, and you say exactly what happens to this pointer into the list, etc. But yeah, if you want to use incorrectness separation logic, you basically have to do this because you have to describe the full behavior here. So either you need to add some kind of mechanism to your language which allows you to do some kind of encapsulation, or you would need some other logic where you don't have these strong guarantees that you actually can reach everything. But yeah, it's an interesting question and something that I'm thinking about and working on right now, because I also want nicer specs than this, because I don't think these kind of specs are nice enough for actually using them. But it also very much depends on what your algorithm is. So in this case, it gets very ugly because something from the outside somehow ended up inside the data structure. But it seems to be some ways to address this.
Great. Let's thank the speaker again.